Hello everyone, my name is Shruti Kachwadkar, student of IIIT DM Jabalpur. This video presentation is about relations and partial orders. It is guided by Professor Aprajita Ojha ma'am, Computer Science and Engineering Department from IIIT DM Jabalpur. So let's begin our discussion with this quote. Mathematicians do not study objects, but relations between objects. Interesting, isn't it? So it shows that how important relations are in the field of mathematics, and therefore we need to understand them properly for understanding the basic concept. We need to understand the basic concepts of relations. So let us begin. The topics which will be covered in this presentation are as follows. We begin with origin, from where the term relations originated. Next we will come to the Cartesian product. Before understanding what relations are, before defining relations, we need to understand what is meant by Cartesian product. Next we define relations. Then we see representation of relations using digraphs. Properties of relations, equivalence relations, what are partial orders will be covered. Then at the end there is a small take home exercise for you guys. There are some useful links provided, and at the end we have references. So origin. The term relation was first given by mathematician A.D. Morgan, who carried out extensive investigation in this domain in the 19th century. According to him, the traditional logic for expression and justification was not adequate enough to express simple arguments occurring in everyday life, and so therefore he wanted another system to express these arguments, simple arguments, properly. He then introduced relations. So in this way relations got introduced. Now in everyday life we come across various kinds of relations. For example, relation between an employee and his salary, or talking about computer science domain, relationships between a program and the variable it uses, etc. So these are all kinds of relationships, and we need to therefore we need to study them properly in order to understand them more effectively. So let us begin defining relations. Before coming to relations, we need to understand what is meant by Cartesian product. So Cartesian product, if there are two sets A and B, two non-empty sets, we define the product set or Cartesian product as the set of ordered pairs A, B, with A belonging to capital A and B belonging to capital B. Okay, so it consists of ordered pairs. Therefore we can write it in this way. If there are two sets A and B, then their Cartesian product A cross B, okay, their Cartesian product A cross B is given. It consists of ordered pairs A, B, such that the first element of the ordered pair belongs to the first set and the second element belongs to the second set. Okay. Similarly, we can define Cartesian product between m number of sets. So Cartesian product A1 cross A2 cross A3 cross up to AM is the set of all ordered m tuples A1, A2, A3, AM, where each AI belongs to the corresponding set. So here the small a1, it belongs to capital A1, small a2 will belong to capital A2, small a3 capital A3, and so on. Small am will belong to capital AM. So this is all about the Cartesian product. Let us look at one example here. We have two sets A and B. Okay, A is having three elements 1, 2, 3, and B is having two elements R and S. So A cross B will consist of all the possible combinations such that the first element belongs to the set A and the second element belong to set B. This is because we are doing A cross B. If we want B cross A, then the first element should belong to set B and second element should belong to set A. So here we have 1R 1S, 2R 2S, 3R 3S. So this is between the two sets. There is another example in which we are having three different sets, languages, memory and OS. So if languages is denoted by L, memory M and OS O. So if we do L cross M cross O, it will contain all the categories that describe a program. So this is just simple logic. Okay, now next move on to defining relations. Now in this presentation particularly we are going to deal with binary relations, that is relations between two sets. So what are binary relations? A binary relation R from set X to set Y is a subset of Cartesian product X cross Y. Binary relation is R, it also consists of ordered pairs, and they form the subset of the Cartesian product X cross Y. Now if we have a single set A, then the binary relation is defined on A and therefore it is a subset of A cross A. For two distinct sets A and B having cardinalities M and N respectively, the maximum cardinality of A and B is M into N. So we know that a relation is a subset of Cartesian product, and if there are two distinct sets having cardinalities M and N respectively, the Cartesian product cardinality will be M into N. Since R is a subset of Cartesian product, the maximum cardinality of R is thus M into N. Okay, so here we have defined binary relations. Now let us see what is domain and range of relations. So if there are two sets A and B, the relation R have ordered pair X, Y. Okay, if there are two different sets A and B, the relation will consist of ordered pairs X, Y. Then the domain of R is the set X. Okay? The domain of R is the set X such that X, Y belongs to R for some Y in B, and the range of R is the set Y such that X, Y belongs to R for some X in A. Okay, so for simplicity you can say that if we are having two sets and the relation will have the ordered pair X, Y, so the first element of each ordered pair, the set of first element forms the domain, and set of the second element that forms the range. So domain and range of relations is clear to you. Next we see one short example here. Let A be a set consisting of 5 elements 1, 2, 3, 4, 5 and R is defined on A as A is related to B if and only if A is less than B. Okay, so this is the relation defined. So according to this relation we have these many number of ordered pairs here. Okay, now what is the domain of R? The set of first elements. So what we have 1, 2, 3 and 4. So domain of R is 1, 2, 3, 4 and range of R is the set of second elements, that is 2, 3, 4, 5. So in this way you can find domain of a relation and range of relations. Now let us see how the relations are actually represented, how we can represent relations. Okay, a relation can be represented using a directed graph. So in order to represent relation we can use directed graph. The number of vertices in the graph is equal to the number of elements in the set from which the relation has been defined. We define a relation on some set. Okay, so the number of elements in that set form the number of vertices in the graph. And now how the edges will be defined? For each ordered pair X, Y in the relation R, there is a directed edge from vertex X to vertex Y. So if there are ordered pairs X, Y, etc., X, Y, A, B, etc. So for X, Y, there is a directed edge from vertex X to vertex Y. If there is an ordered pair X, X, okay, so there will be a self loop on the vertex X. Okay, so in this way we can represent relations using digraphs. So let us see one example. If we are having a set A, 1, 2, 3, 4 and relation is given as follows, then the digraph it will be as follows. 1, 2, 3, 4 vertices will be there. and these are the edges. Okay, so these are the various edges. Since we have 1 comma 1, there is a self loop here. We have 1 comma 2, so there is a directed edge from vertex 1 to vertex 2. We have 2 comma 1, so there is another directed edge from vertex 2 to 1. 2 comma 2 we have self loop. 2 comma 3 we have a directed edge here. 3 comma 4 again we have a directed edge, and 4 comma 1 we have this directed edge. Okay, so in this way we represent relations. Now there is a short exercise for you. In this, it is given that let A equals to ABCD and let R be the relation on A that has the matrix this. Now another way of representing relations is through matrix. So it is the number of elements in the set. The matrix, so columns are the number of elements and rows are the number of elements, and if there is an edge, if they are related, we have one in that place. So here we are having the rows are A, B, C, D, columns are A, B, C, D. Since here it is 1, which means that A comma A is present in the relation. Okay, A comma B is not present in the relation. So in this way we represent relations in the matrix. We have one for those at those places which which ordered pairs are present in the relation, we have 1 there, and if the ordered pair is absent, we have 0 there. So okay, so now what you have to do, construct the digraph of R and list in degrees and out degrees of all the vertices. I hope you know what is meant by in degrees and out degrees, so you can do this easily. Just try it. Okay, now we come to next topic, which is paths in relations and digraphs. So that now since we have seen, we know that relations can be represented using digraphs. Now suppose that relation R is a relation on a set A. Okay, so what is path? A path is of length n in R from vertex A to vertex B, or talking from some point A to B, is a finite sequence pi, which is given by A, and there are middle various elements x1, x2, xn minus 1 up to B, beginning with A and ending with B, such that A is related to x1, x1 is related to x2, and so on, xn minus 1 is related to B. Now to visualize this, what is actually path, you can visualize it very easily with the help of digraph. So the length, thus the length of path is the number of edges in the graph. How many number of edges you are having, that forms the length, of the path, where the vertices need not all be distinct. Okay, so there is an example. We'll see here how the paths are defined. So we have this directed graph here. So path 1, it is represented by pi 1, pi 2, pi 3. So first path we are representing it with pi 1, 1, 2, 5, 4, 3. So 1, 2, 5, 4 and 3. So it is a path from vertex 1 to vertex 3, and middle elements are 2, 5, 4, such that 1 is related to 2, 2 is related to 5, 5 is related to 4 and 4 is related to 3. Similarly we have 1 to 5, 1 and we have 2 to 2, so there is a self loop here. Now the concept of path actually it is used for connectivity, to show whether which elements are connected. So if n is a fixed positive integer, we define a relation r to the power n on A as follows: x is related to y means that there is a path of length n from x to y. So if we define r, we define a relation r on r to the power n on A such that the two elements are related if there is a path of length n from x to y. So similarly there is a concept of r to the power infinity. So if we write, we can define a relation r to the power infinity such that x is related to y if there exists any path between the between x and y in the digraph. So this concept is actually used for the to find whether the two vertices are connected or not. So it is used in the concept of connectivity. Okay. Next we will see what are the properties of relations. Okay, what are the various properties of relations. Now relation satisfies certain properties which are as follows. The first is reflexive property, irreflexive property, symmetric property, antisymmetric property, asymmetric property, and we have transitive properties. So there are various properties. Let us see what are those one by one. So we begin with reflexive and irreflexive relations. Okay. So what is a reflexive relation? A relation R on a set A is reflexive if A is related to A, if A comma A belongs to R for all A belongs to A. That is, A is related to A for all A belongs to A. It means that each and every element of a set A should be related to itself. So okay, so there should, talking in terms of digraph, there should be self loop on every vertex, because every element of A should be related to itself, then only the relation is said to be reflexive. Now a relation on the set A is irreflexive if A is not related to A for every A belongs to A. It is just opposite to reflexive. So a relation will be irreflexive if and only if there should not be even a single element which is related to itself. So talking about in terms of digraph, relation is irreflexive. For a relation to be irreflexive, there should not be self loop on any of the vertex. Okay, so reflexive. Thus R is reflexive if every element A belonging to A is related to itself, and it is irreflexive if no element is related to itself. So a relation can either be a reflexive relation or it can be an irreflexive relations. It cannot be both at the same time. So the intersection is phi here. If a relation can either be reflexive or it can be irreflexive. A reflexive relation has cycle of one and every vertex, while so we have already seen this. Next we will see what are symmetric, asymmetric and antisymmetric relations. So a relation R on a set A is symmetric if whenever A is related to B, then B should also be related to A. Okay, it then follows that R is not symmetric if we have some AB which belonging to A with A related to B but B not related to A. So it should contain so symmetric is simple. If A is related to B, then B should also be related to A. That is, if A comma B is present in R, B comma A should also be present. Now what is asymmetric? A relation R on a set A is asymmetric if whenever A is related to B, B should not be related to A. It is just opposite to symmetric. So if A comma B is present, then B comma A should not be present for a relation to be asymmetric. Next, a relation on a set A is antisymmetric if whenever A is related to B and B is related to A, then A should be equal to B. Okay, so don't worry, these are just the definitions. We will understand each and everything with the help of examples. So you'll understand, you don't worry if you're not understanding now, you'll definitely understand with the help of example, which we will be just looking at. So next, let us see what is meant by transitive relation. A relation R on a set A is transitive if whenever A is related to B and B is related to C, then A should also be related to C. That is, if A comma B is present and B comma C and some B comma C is also present, then the relation should also have A comma C. Okay, but if no such ABC exists, that is, if we have in a relation we have A comma B and there is no ordered pair starting with B. Okay, so there is no such condition, so definitely then it is transitive, then R is transitive. Now we have seen all the properties, and therefore we can let us have a look at one example which will help you. Okay, so these are various relations. Let us look at the first one. We need to determine whether it is reflexive, irreflexive, or antisymmetric, symmetric, or transitive. So what is there? First relation, it consists of set A has 1, 2, 3, 4. For a relation to be reflexive, every element should be related to itself. That is 1, 1, 2, 2, 3, 3, 4, 4 should be present. And as you can see, these ordered pairs are present. Therefore, it is reflexive. Okay, since it is reflexive, it cannot be irreflexive. Now let us check for symmetry. 1 1 is present, so 1 1 is present, it is not a problem. 1 2 is present, so 2 1 should also be present, so it is present here. 3 4, then 4 3, it is present here, so it is symmetric. As it cannot be asymmetric, it is not antisymmetric also, because if 3 4 and 3 4 is there, 4 3 is there, and 3 is not equals to 4, so it is not antisymmetric. Let us check for transitivity. 1 1 if there is 1 1 and there is 1 2 and there is 2 1, so 1 1 should also be present, and 2 2 should also be present, which is there. Then 3 4 and 4 3, 3 3 should also be present, 4 4 should also be present, which is there. So it is reflexive, symmetric, and transitive. Similarly, you can see the other examples also. Here you can see that it is not reflexive. Sorry, there is a mistake here. It is not reflexive because 4,4 ordered pair is not present here. Okay, and it is symmetric. It is also antisymmetric because 1 1 and 1 1, both the elements are equal, and also it is transitive. It is not reflexive. I'm sorry, here by mistake it happened. Okay, and the third example, r equals to 5. Now it is not reflexive because none of the element is related to itself, so it is not reflexive. But it is irreflexive because no element is related to itself, therefore it is irreflexive. It is symmetric because there is no such condition that if a comma b is present, if a comma b is present, then b comma a should be present. If it is not, then it is not a problem. So it is symmetric, it is asymmetric also, it is antisymmetric also, and it is transitive also. So except reflexive property, it satisfies all the properties. So you can try for these two examples on your own. Okay, I hope you understood how we are doing it. Okay, now since we have seen various properties of relations, we can define what are equivalence relations and partial order relations. So these two actually form very special kind of they are very special relations, and they are useful in mathematics. They have very important applications in mathematics. So a relation R on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. A relation R, we can say that a relation R is an equivalent relation if it satisfies three important properties, which are reflexive, symmetric, and transitive. A relation R on a set A is called a partial order if R is reflexive, antisymmetric, and transitive. The set A together with the partial order R is called a partially ordered set, or simply a poset, and is denoted by A comma R. Okay, so I hope the definition is clear to you. Now a poset, we can so poset, we are defining one more kind of which is actually a poset itself. So a poset A comma R is called a totally ordered set if every pair of elements in A are comparable. That is, we take any elements from A, we take any elements A comma B, there should exist some relation between them. So either A should be related to B or B should be related to A, but those two elements should be related. So such posets are known as totally ordered set. So these are just the definitions. We are going to discuss them in just brief. Okay, if you want to learn more, there are useful links provided. You can visit them and you can learn about them in detail. Let us look at one small example here. We have set A consisting of three elements 1 2 3. The relation is given by 1 1 2 2 3 3. Okay, this is the relation which is given. Now you can see that for a relation to be equivalent, it should be reflexive, symmetric, and transitive. As you can see, every element is related to itself, so it is reflexive. Okay, it is symmetric because these are the diagonal elements. So it is symmetric also, and therefore it is and it is transitive also, and therefore it is an equivalence relation. Also, it is a partial order relation because reflexive and transitivity is already satisfied. It is also satisfying antisymmetric properties. So this is the only relation which is both equivalence and partial order. Okay, because it satisfies all these properties: reflexive, symmetric, and transitive, therefore it is equivalence; reflexive, antisymmetric, and transitive, therefore it is partial order relation. Now here is an exercise for you guys. Okay, take home exercise. These are some questions, you can try them. They are not very difficult questions. Let us see the first one. Given a set A, okay, consisting of n elements, a relation R is defined on set A. How many reflexive relations are possible? Okay, how many reflexive relations are actually possible here? So I hope you will be able to do this. Just let us discuss it in short. Now, since relation is a subset of Cartesian product, we are having relation from A to A. So the cardinality of A cross A will be n cross n, that is n square, since A is having n elements. Now, we know that for relation R to be reflexive, each and every element should be related to itself, that is 1 comma 1, 2 comma 2, 3 comma 3, and so on, n comma n should be present in the relation. Now how many such pairs will be present? N such pairs will be present in R for R to be reflexive. Therefore, for these n tuples have only one choice, that is to be present in the relation, and the rest n square minus n elements, they can either be present or they can be absent. So they have two choices. So two choices for n square minus n. So we have so in this way we get that reflexive relation, number of reflexive relations which are possible are 2 to the power n square minus n. So in similar manner you can try these rest of the questions. Okay, here you can see that how many reflexive relations are possible. So we have this, R is on set A, cardinality of A is n, so relations are subsets of A cross A, therefore we have cardinality of A cross A is n square. So total number of subsets of the set containing n square elements is given by 2 to the power n square. Now reflexive relation should contain these ordered pairs, and n such ordered pairs will be present. So they have only one choice. Remaining have remaining have two choices. So how many elements are present? How many remaining elements are present? N square minus n. Therefore we have total 2 to the power n square minus n number of reflexive relations. Okay, so here we conclude our discussion. Now actually this presentation is just an introduction part. If you want to learn more about what are partial orders, how they are represented, so they are represented using Hesse diagram, and later the concept of lattices come. So to study all those concepts, you can refer to these links. These are some useful links. Okay, and these were the references from which the material and content of this presentation was taken. I hope you understood whatever we discussed here, and thank you for watching. Thanks.